We will wait for few more minutes and we'll start at around 7:10. Hello everyone, welcome to the fourth introduction session of the NPTEL course Atomic and Molecular Physics. Today in this session we will be discussing about week 4 lectures. Myself Vivekananda Nayak. I am a PhD research scholar in the Department of Energy Science and Engineering, Indian Institute of Technology, Delhi. So, in this week's content, must have you must have read about the magnetic dipole moment, which mm, as a result give rise to vector atom model of the vector model of the atom. So basically, what happens? So from Bohr-Sommerfield's structure of atom, we came to know about new quantum number k, which was known as azimuthal quantum number or orbital quantum number. So here, as we can see, when an electron revolves, according to Bohr, electron is revolving in a circular orbit, but according to Sommerfeld, the orbits are not exactly circular, but they are elliptical. So that gave rise to another quantum number. So we had two quantum numbers n and k, where k is less than equals to n. Suppose here in this case an electron revolving in a circular orbit of radius r with velocity v, then due to the negative charge of the electron, the orbital magnetic moment L vector will be directed opposite to the magnetic dipole orbital angular momentum vector L will be directed opposite to the magnetic dipole moment mu L. So basically we can derive the orbital magnetic dipole moment from this relation mu is equal to Ia, because when an electron revolves in a circular path, it results in a current, and a current loop results in the formation of a magnetic field. So, as a result, we have magnetic dipole moment. So, there are two different type of magnetic dipole moment. One is orbital, and another is spin. Orbital is the orbital motion of the orbital dipole. Orbital magnetic dipole moment is due to the orbital motion of the electron, while the spin magnetic moment is the spin motion of the electron. So, from the formula, the magnetic dipole moment is by mu is equal to Ia. So from this formula we can derive, which which has already been taught in the class. So basically, so we can derive mu L by L, where we are taking the magnitude of mu L, because only then it will be E by 2m. So as you can see, L vector and mu L vector both are in opposite directed. So the general equation is of the form mu L vector divided by L vector equals to minus E by 2m, which is again due to the negative charge of the electron. So basically, this gives the magnetic dipole moment produced to the orbital angular momentum. So this ratio is known as gyromagnetic ratio or gyromagnetic ratio. Now, if we put the value of L, basically from quantum mechanics, we know that L vector is equal to L vector mod is equal to L into L plus 1 root into h cross. So if we put all this value here, h cross is nothing but h by 2 pi. So if we put all the values, so we get a relation in terms of mu b, where mu b, from this relation we can calculate, if we put L here. So basically it will be in terms of mu b, where mu b is eh by 4 pi m or eh cross by 2m, which is called as Bohr magneton, and it is the unit of and it is the unit of a magnetic dipole moment. So Bohr magneton can also be written as Eh cross by 2m. So putting the value of Me, that is mass of electron, and h cross, we get the value of the Bohr magnet is 9.27 10 to the power minus 24 ampere meter square. So now also, due to the orbital motion, there is space quantization, that is the uh, orientation of the orbit, or the orientation of the orbit in which the electron is revolving is also quantized. So the, like in this case, the direction is along L, the direction is along this. Suppose if you take it as a z axis, then direction is along z axis. But however, if there are any external magnetic field applied, suppose the magnetic field applied in the direction, that is z direction, then due to this magnetic field there will be interaction between the orbit, energy orbital. So that's why, so as a result the orbital will be rotated in different orbits will be rotated in different planes. So corresponding to these, we have different values of the direction of the orbit. Suppose if the orbit is like this, so the direction will be along this, and if the orbit is like this, then the direction will be along this direction, and also it can be along this direction. So like this, we have different values of the direction, and that is known as phase quantization. And again, after the discovery of electron spin, then we also came to know about different other formulas. Like for, if we talk about spin, then for spin we take mu s vector by s vector, which is e by 2m, where mu vector amount e by 2m, we did t2e by 2m, or e by m. Here gs, which is g factor, which is 2 for, sorry, this g factor is 2, the value of the g factor is 2 for spin. But however, here as you can see, the value of g for orbital angular momentum is 1. So mu l by l is minus e by 2m, but mu s by s is e by 2m, and other rules are also same. So s vector mod is nothing but s into s plus 1 root h cross, and the z component is quantized. So z vector will be, so sz is component of the s vector, which is ms h cross. So like in the previous case, corresponding to particular l value there are different ml values. Similarly in this case, corresponding to particular s value there are different ms values. For s is equal to half, we get ms is equal to plus minus half, that is, we have 2s plus 1 values. So due to the due to the magnetic dipole moment coming from the orbital motion as well as spin motion, then they couple together and result in the formation of a total um, result in the formation of a new quantum number, which is total angular momentum quantum number, which is j, where j is equal to, j vector is equal to l vector plus s vector. So that more or less explains the explains the study behind the vector model of the atom. Now we will discuss about few problems based on these concepts. So the first problem is, a beam of electrons enters The problem gives, a beam of electrons enters a uniform magnetic field of magnetic field strength is given as 1.2 Tesla. So calculate the energy difference between the electrons whose spins are parallel and anti-parallel to the field. Here it is given that use standard values of mass of electron, charge of electron, and Planck's constant. So basically, here in this question, it is given that the beam of electron is present in a uniform magnetic field. Then we have to calculate the energy difference between the electrons whose spins are parallel and anti-parallel. Because as we see here, so when there is a magnetic field, then the orbital will be rotated in different directions. Similarly, in case of in presence of the magnetic field, the spin motion is also affected, and due to the magnetic field and the spin magnetic moment, due to the interaction between the magnetic field and the spin magnetic dipole moment, it results in the change in energy, and that energy we need to calculate. Because if the electron spins are different, that is parallel and anti-parallel, where parallel is along the magnetic field, which is, if this is magnetic field is applied in this direction, so spin of the electron, we know that spin of uh, for electron S is equal to half. So there are two different spins, one is minus half and another is plus half. So plus half is, it is parallel to the magnetic field, and minus half is anti-parallel to the magnetic field. So here in this question we will see, if the electrons, if the spin of the electron is different in the same magnetic field, then what will be their energy difference, because due to the interaction between the magnetic field and electron spin, spin magnetic moment, there will be change of the energy of the electron. So basically what we know, the intrinsic spin angular momentum of electron is given by s vector. So basically what we know, we know, as I discussed, mu s by s is E by m, because for spin Gs is equals to 2. So mu s by s is equal to 2E by 2m, or 2, and s vector mod is given by s into s plus 1 root into h cross. So here, calculate the energy difference between the electrons. So for electron S is equal to half. So now what we will calculate? If we calculate the Z component, then from this above relation we have mu S is equals to E by M into, we have mu by, sorry, here S will be in that side, so we will get mu S is equal to E by M into S. So for S is equals to, so this gives the total spin, magnet dipole moment for Z component. We can write mu s Z is E by 2m, E by m into sz, and I just tell you that sz is nothing but ms h cross. So if we put here, so it will be E by m into ms h cross. But here ms, there are two different value of ms, because for h is equal to half, ms is equals to minus half and plus half. So due to these two different value of ms, there will be two different value of mu sz. So what will be the mu sz value? The mu sz will be, so mu sz, that is the z component of spin magnetic dipole moment, is E by m into h cross ms. So if we put here plus minus half, then it will be plus minus E by m into h by 2 pi into half. So it gives plus minus Eh by 4 pi m. So this is the z component of magnetic. This is the z component of spin magnetic dipole moment. Now due to this the spin magnetic dipole moment, when we place the when the electron enters, so when the electron enters a magnetic field, then it will experience of energy, and that interaction energy is given by, what is the interaction energy between magnetic field and the magnetic dipole moment. It will be minus mu s vector dot b vector. So if the electron spin is parallel and anti-parallel, then the energy will be plus minus half, because here mu s is, here plus minus is here, but here it is minus mu s vector dot b vector. But we know that due to spin, due to the charge of negative charge of electron, so if the electron has spin half, that is the spin is in this direction, then its magnetic moment will be in opposite direction, which is mu s. But if the spin of the electron is anti-parallel, then magnetic moment will be opposite to that. So the in relation, this minus sign and the minus sign involved here between the direction of s and mu s get cancels out, and we get total the energy shift due to the interaction between the magnetic dipole moment and magnetic field is Eh by 4 pi m into b. So this is the interaction energy of the electron which has spin half. So for parallel, what we will get, so if the spin is half, that is spin is along the direction of magnetic field, then mu m will be how much? It will be Eh by 4 pi m b, and similarly for antiparallel the value will be Eh by 4 pi m b. So here in this question it is given that calculate the energy difference. So what will the energy difference? Then the total energy difference between the two energy, the energy of the two electron will be Eh by, it will be minus because it is antiparallel. So Eh by 4 pi m into b minus, this is minus Eh by 4 pi m into b. So the total energy difference will be how much? It will be EHB by 2 pi m. So due to different direction of spin, the force experienced by the two electrons in presence of magnetic field is different. So the energy is different. So for one electron the energy will be positive, and for another electron the energy will be negative. So due to the different in direction of the spin, some will gain energy in case of a magnetic field, but another electron will lose energy. So that's why the energy will be different. So the two energy, when we calculate the difference in energy, then the energy difference will be EHB by 2 pi m. So what is given? Use standard values of mass of electron, charge of electron, Planck's constant. So if we put here, so delta um is equals to EHB by 2 pi m. Then if we put the value of E, which is 1.6 into 10 to the power minus 19 coulomb, and B is 1.2 Tesla, 1 point V is 1.2 Tesla, and mass of electron is 9.1 into 10 to the power minus 31 kg, and H is 6.64 into 10 to the power minus 27, 10 to the power minus 27 joule into second. So if you put all these values, you can calculate the energy difference. So can you please calculate the value for me? The values of the E, B, M and H, and H we know, we already know these values. So can you calculate the value in terms of joule and then convert it in terms of electron volt? So can anyone calculate and say me the answer? Uh, H is 10 to, sorry, 10 to the power minus 27. I sorry, I wrote it in terms of not joule. So for joule, the value will be 10 to the minus 34. But for orb, it will be. Thanks for pointing it out. So basically, it will be 10 to the power minus 34 joule into second. But in terms of if we convert it into CGS unit, then orb into second, it will be minus 27. So anyone? Yes. Hello. Yes. Speak. So basically, the answer if we write it in electron volt, so the it will be the value 1.39 into 10 to the power minus 4 electron volt, not joule. If we convert it to electron volt, so what we learned in this question is if if the two electron have different spins, then due to this spin of the electron, the energy of the two electron will be different. So as a result, in case of transitions, we will get different transitions. Like um, in case of both in case of Bohr's model, getting that the energy levels are separate and it depends only upon the value of n. So the spectral lines we are getting, for example, if we consider the hydrogen spectrum, then there was Lyman series, Balmer series, etc. But when we saw these series in a spectrometer, we found that with high resolution, each spectral line consists of different other lines. So since we know that the one line corresponds to one energy difference, so if there are many lines, so there will be many other energy levels which were not given by Bohr. So as a result, if we so as a result, as we went towards more quantization, so as a result of the quantization of different, like here we study about space quantization, like so then due to different quantization, there are different quantum numbers and there are different values of energy, and as a result, we are getting different transitions. So basically, here we found that since here there is no discussion about orbital magnetic moment, so we are getting spins, because here in this question it is given that whose spins are parallel and anti-parallel to the field. So in this case, we know that electron is a spin half particle, or the also we know we call it as fermion. So for h is equal to half, we have two values of ms, which is minus half and plus half, and the dipole moment, the z component of the magnetic dipole moment, which is given by ms h cross. So if we put the value, because the z component is quantized, so for z component we got the value mu sz is plus minus eh by 4 pi m. So the electrons which have different spins, that is the direction is different, one is parallel and another electron is anti-parallel. So due to their different direction, so they will experience different force, and so as a result their energy will be different. So the electron which was parallel to the magnetic field will gain energy from the magnetic field, and it will the energy will be by 4 pi m, in positive Eh by 4 pi m into V, but for electron in antiparallel the energy will be minus by 4 pi m into B. So the difference in energy will be B by 2 pi m. So if we put all these values, so the energy difference between two electrons is 1.39 10 to the power minus 4 electron volt. So I hope um, uh, is there any doubt in this question? Anyone? I can explain it again. Okay, then let's go to the next question. Here, in this question, it is given that calculate the two possible orientations of spin vector S with respect to the magnetic field direction. So, like it is nothing but the space quantization here. So basically, what is space quantization? Now, when there is a magnetic field, then there are different orientation of the spin vectors. So we want to calculate different spin vectors, because here it is given that calculate two possible orientations of spin vectors. So since two possible orientations, so what we have? So we have 2s plus 1 equals to 2, because a spin vector s have 2s plus 1 orientations. So since it is given two possible orientations, so for in this case 2s plus 1 equal to 2, so from which we get s is equal to half. So here the spin is half. So if we consider is spin magnetic quantum number, it is ms, which is plus minus half. So corresponding to s, there is two quantum numbers which is plus half and minus half. So like in this case, L is called as orbital quantum number and ml is called as orbital magnetic quantum number. So here ms is spin and s is spin and ms is spin magnetic quantum number. So due to this spin magnetic quantum number, there will be two different orientations of the spin vector in case of magnetic field. So basically, if s vector is equal to s into s plus 1 root into x cross, and the z component which is sz, the magnitude of sz is ms h cross. So if the angle between S and MS, so here due to the angle between the applied magnetic field, because the magnetic field applied is in z direction, so B vector is in z direction, but the spin is at some angle which is theta S vector. So in this case, what will be the angle between the z component? Because since s is directed in this direction, the sz component will be directed along the magnetic field. So the angle between the spin vector and the z component is, we can, if cos theta is the angle, if theta is the angle between spin and sz, then what we will get? We will get cos theta is equals to sz by s, because so this is the relation between, this relation will be used to calculate the orientation, because cos theta is equal to sz by s gives the value of theta. So if we put, then theta will be cos inverse sz by s. So we know that sz is nothing but ms h cross, and s is s into s plus 1 h cross. So h cross gets cancelled out, and for two different values, since ms has two different values, that is plus minus half, so in this case we will get two different theta. So for one case, theta is cos inverse. If we take half, then in that case what will be theta? Theta will be cos inverse half divided by s is also half, So half into half plus 1 root over. So here it will be root over. So it will be cos inverse 1 by 2 divided by, what will be the value? Half into 3 by 2, which is 3 by 4. So it will be 3 by 2. So what will be the value? Because it will be ms is equals to half and s is equal to half into half plus 1. So 1 by 2 into 3 by 2, 3 by 4. So root is root 3 by 2. So if we put this, then it will be cos inverse root 3. Theta is equal to cos inverse root 3. So what is the value of theta then? For what is the value of theta? Cos inverse root 3, how much? 991 tell. Cos inverse root 3 is how much? So the value of theta will be 54.7 degree. We calculated here for ms is equals to half. Similarly, if we calculate for ms is equal to minus half, it will be minus 1 minus root 3. Then simply we can write. So if 1 is theta, let me add another slide. So similarly, if we take ms is equals to minus half, then what will be theta? Then theta will be cos inverse ms by s into s plus 1 root. Then it will be cos inverse. So everything is same as previous case, but here there will be negative sign. So minus half by root 3 by 2. So it will be cos inverse minus root 3. Then what will be the value of cos inverse minus root 3? It will be nothing but since if you take it as theta 1, then simply it will be 180 minus theta 1. So it will be around 125.3. So we got two possible orientations. So then what will be the, then if this is magnetic field which is applied along the z direction, then one will be, for 1 theta it is how much? 54.7. So there will be one which will be the angle between, it will be theta 1, which is corresponding to ms is equals to half. There will be another, sorry, the two will be same because their magnitudes are same. It will be, this is minus z direction, it will be ms for minus half, and the total it will be theta 2. So theta 2 is 120. 5.3. So due to dip- mm, due to different spins, because for s is equal to half, there are two different spin, and uh, so due to two different spins, there are two different orientations of the spin orbital magnetic moment, and corresponding to the this corresponds to the ms value of minus one plus 1 by 2, and this corresponds to the ms value of minus 1 by 2. So there are two different orientations, and these are the two values of the orientations. Everyone is clear about this problem? Have any doubt, you can discuss with me, because if you don't ask any doubt, then you will not also enjoy this, because these are interesting things in atomic, and in atomic molecular physics mainly these spin orbital magnetic moments coupling, these are mainly interesting and most important. Also it comes in different exams, so if you don't ask any questions, then your doubts will not be solved then. Then the next question gives, calculate the possible orientations of the total angular momentum vector j corresponding to j equal to 3 by 2 with respect to a magnetic field along z axis. So this is very similar to the previous question. Can anyone tell how we'll solve this question? Just as the previous problem, we solved the different orientations, we calculated different orientations. It is same, but it is with total angular momentum vector j. So can anyone tell me what will be the process of solving this problem? How we will go with this problem? So basically, what we will do, we know that for, like in case of here, as I discussed here, L is L into L plus 1 root h cross, and ML, and the Z component is ML h cross. So similarly for S and J, for J also, if we consider J, then J vector mod will be L into, sorry, not L, it will be J. So for J vector, it will be J into J plus 1 root h cross, and its j component will be jz. It will be mj h cross, where mj will be how much? It will be minus j2 plus j. So here, given that j is equals to 3 by 2, then what will be values of mj, and there will be how many values of mj we will get for corresponding to j is equals to 3 by 2? Anyone speak loudly? Sorry, not two. We will get four values, because as we discussed, for s there are 2s plus 1 orientations, or 2s plus 1 values of ms. So in previous case s was half, so ms was minus half and plus half. So how we get minus half and plus half? Because for s equal to half, if we put s equal to half here, it will give two values. So for s equals to half, there are two values of ms, which is minus s2 plus s, with increment of 1. So here minus s is minus half, plus s is plus half, so we get only two values. But here in this case, since j is equal to 3 by 2, we will get how many values? We will get 2j plus 1 values. So for j equal to 3 by 2, what is 2j plus 1? For j equals to 3 by 2, what will be 2j plus 1? 2j plus 1, what will be 2j plus 1? For j equals 4, for j equals 3 by 2, it will be 4. So there will be 4 values of mj. So they will be plus minus 3 by 2 and plus minus half. That is minus 3 by 2 minus half plus half and plus 3 by 2. There are So corresponding to j is equal to 3 by 2, there are 4 values of mj. So as in previous case, theta was cos inverse ms by s into s plus 1 root. Similarly here, what will be theta? Theta will be cos inverse mj divided by j into j plus 1 root over. Then here j equals to 3 by 2 and mj equals to minus 3 by 2 minus half 3 by 2. So corresponding to 4 mj values, we will get 4 theta values. So what will be the values of theta 1, theta 2, theta 3, theta 4? Please calculate and tell me. Suppose for theta 1, we will take mj equals to minus 3 by 2. Then it will be cos inverse minus 3 by 2 by j into j plus 1 will be same, because j is equals j into j plus 1 will be same for all the 4 cases. So for j equal to 3 by 2, j into j plus 1 root will be 3 by 2 into 3 by 2 plus 1 root over. Please mute yourself. So it will be 3 by 2 into 5 by 2. So it will be 8 by, sorry, 15 by 4 root over. So it will be root 15 by 2. So it will be root 15 by 2. So it will be minus 3 by root 15. So can you tell me cos inverse minus 3 by root 15 will be how much? So it will be, we can take it at 39.2. So this will be 39.2. So if this is 39.2, then if we take uh, minus, if we take plus 3 by 2, then what will be the, if we take plus 3 by 2, then it will be cos inverse 3 by 2 by root 15 by 2. So it will be 3 by 15. So for 3 by 15, it will be 180 minus 39. So it will be 180 minus 39.2. So the value will be 140.8. Similarly, if we take mj is equal to plus minus half, then it will be cos inverse 1 by root 15, what will be its value? Then another will be cos inverse minus 1 by root 15. Then what will be these values? Please calculate and tell me. So for cos inverse 1 by root 15, it will be 75, and for cos inverse minus 1 by root 15, it will be 180 minus 75, which is 105. So for different mj values we get different orientations, and so the four orientations are: one is 39.2, one 40.8, 75, and 105 degrees. So there are four orientations corresponding to each j value. So since j equals to 3 by 2, there are four mj values, because like in this previous case we found two possible orientations of spin vector s. So since 2s plus 1 gives the number of orientations, for s equal to half we have two orientations, because for s equal to half the value of 2s plus 1 equals to 2. Similarly for j equal to 3 by 2, the value of 2j plus 1 is 4. So there will be four values of mj, that is minus j to plus j. So minus 3 by 2 to plus 3 by 2. So minus 3 by 2 minus half, half and 3 by 2. So corresponding each value of mj, there will be each orientations of the orbital magnetic of the total total orbital total angular momentum of quantum number. So total will be, suppose this is magnetic field B, then there will be four, that will be in this direction one, in this direction one, in this direction one, and this direction one. So it will be, they all will be of same magnitude, because only theta are different but j value is same, and the magnitude of j vector depends on the value of j, because the magnitude of j is j into j plus 1 h cross. So for each j value, the magnitude of j vector is same but the z component value is different, so due to which their orientations are different. So these or the length will be same but orientations, that is the value of theta, will be different. Then next question, the question gives: determine the normal G-man splitting of the cadmium red line of 6438 angstrom when the atoms are placed in a magnetic field of 0.009 Tesla. So can anyone tell me what is normal G-man? What is G-man effect? You must have you must have seen the lectures in the week 4 lectures. So what is G-man effect? Can anyone tell? In which field we can see G-man splitting? Electric. So when an atom is placed in the external magnetic field, so as you know that due to the modified quantum numbers, that is spin angular momentum and orbital angular momentum quantum numbers. So when an atom is placed in an external magnetic field, so the magnetic field will interact with the magnetic dipole moments, and as a result there will be energy, and due to these different energies there will be different splitting, because the transitions depend upon the energy values of the two levels in which the transition is occurring. So due to the G-man effect, the energy level splitted into one energy level will be splitted into more than one levels. So as a result, there will be splitting of the spectral line. That is, if the atom was not placed in a magnetic field, there was one spectral line. Here the spectral line is given the initial, before applying external magnetic field, the spectral line was of wavelength 6438 Armstrong. But when we placed in a external magnetic field, then the spectral line gets splitted. However, here it is given that normal G-man splitting. Can anyone tell me there are how many types of G-man effect are there? Types of G-man effects. There are two types of G-man effect. One is normal G-man effect and another is anomalous G-man effect. However, you will read about it in upcoming lectures. So basically, normal G-man effect is uh, here S is equals to 0. That is, no spin is considered. But anomalous G-man effect is there is consideration of spin. In case of normal split, in case of normal G-man effect, one single spectral line. Suppose this is magnetic field is 0. Suppose B vector is 0 here. If S is equal to 0, then if we keep it in external magnetic field, that is B non-zero, then this one spectral line will be splitted into three different spectral lines. The central one will not be shifted, but the two other will be shifted in two opposite directions. Like in this case, in the first problem what we studied there will be energy difference. So this energy difference is EH cross by 4 pi m B. One is positive, another negative. So here also in this case we are considering about spin, but in this case we will consider only orbital magnetic moment, because for normal G-man effect the spin of the electron is not considered. So basically here in this case take only about we will consider about the orbital magnetic moment. So here in this question it is given that the cadmium red line is splitted in due to normal G-man splitting. The cadmium red line of 6438 Armstrong is splitted when the atom are placed in a magnetic field of 0.009 Tesla. So we want to calculate the G-man splitting. So basically we want to calculate delta lambda. So suppose in spectrometer we suppose this is the spectrum, we saw these three lines. So what will be the splitting? Because it will be delta lambda and it will be delta lambda. The central one will be lambda 0. So the right hand side will be lambda 0 plus delta lambda, and the left hand side will be lambda 0 minus delta lambda. So we will calculate delta lambda. So what will be the value of delta lambda? Basically, the corresponding to a particular value of lambda, there is a particular energy. So for lambda, what will be the energy? Because since E is equals to h nu, then in terms of wavelength we can write it as hc by lambda. So since we want to calculate delta lambda, so we want to calculate delta E, because due to change in energy or energy difference there will be change in wavelength. So if we calculate from this relation, since E is hc by lambda, if we differentiate it, then it will have, then what will be, then it will be dE. D will be nothing but, what is the derivative of 1 by lambda? What is the derivative of 1 by lambda? Minus 1 by lambda square into d lambda. So minus hc by lambda square into d lambda. So here we want to calculate the G-man splitting. So we want to calculate delta lambda or magnitude of delta lambda. So we will neglect the negative sign here. So delta lambda will be how much? Because delta lambda can't be negative. Delta lambda, the value of delta lambda is positive, but the positions are different due to different energies. So one will be lambda minus delta lambda, another will be lambda plus delta lambda. So the delta lambda value will be given by lambda square by hc into de mod. So here what will be the value of de in this case? What we calculated, in this case we find here, we calculated um is minus mu s dot b vector by minus mu s dot b vector by, so minus mu s dot b vector, so it was plus minus eh by 4 pi m b. So basically here we will take only one value, because so similarly in this case the de will be how much? De will be eh cross by 2m eh by 4 pi m b. So which is, what is eh by 4 pi m, what it is called? What is EH by 4 pi m? Can anyone tell? It is Bohr magneton, which is mu b. What is the value of Bohr magneton? What is the unit of Bohr magneton? What we discussed in the first slide. Here, what was the unit? Here the unit was ampere to meter square. But here in this relation, if we consider this relation, then what will be the unit of Bohr magneton? Bohr magnet will be, if E is in electron volt and B is in Tesla, then what will be the unit of Bohr magneton? So Bohr magnet will be electron volt per Tesla. So if we convert the value of Bohr magnet in electron volt per Tesla, then we will get 5.79 into 10 to the power minus 5 in the electron volt per Tesla, because ampere per meter square is same as electron volt per Tesla, because since this we calculated mu is equals to I into A, so the unit was ampere into meter square. But here, since we are calculating mu b in terms of energy and magnetic field, so it will be energy per magnetic field. So mu b value in terms of electron volt and Tesla is 5.79 into 10 to the power minus 5 electron volt into Tesla. So here when we multiply b, because b is given in terms of Tesla, so b will be 0.009 Tesla. In Tesla gets cancelled out. Then what will be the energy difference? Can anyone tell me what will be the energy difference? So when we multiply this, we will get 5.21 into 10 to the power minus 7 electron volt. So since the value of D is 5.21 into 10 to the power minus 7 electron volt, so we got the value of D1. Then from this value of DE, we can get the value of del lambda. So del lambda is, in terms of Armstrong, it is 6438 into 10 to the power minus 10 square into D is 5.21 10 to the power minus 7, 5.21 into 10 to the power minus 7 divided by Hc. So Hc can be, in terms of electron volt and Armstrong, we know the value of Hc is 1240. So it will be 12.4 into 10 to the power 3 electron volt into Armstrong. So Armstrong, one Armstrong, and here another Armstrong, it will get cancelled out. So there will be only one remaining Armstrong, because electron volt gets cancelled out. So it will be 1.73 into 10 to the power minus 3 Armstrong. So what we found? So if for a cadmium red line, if there were only single line of wavelength 6438 angstrom, and when we keep it in a external magnetic field of magnetic field strength 0.009 Tesla, then due to the effect of normal Zeeman splitting, the splitting will be in three lines. So this central line will be 643 angstrom, but the two lines will be displaced by 1.73 10 to the power minus 3 angstrom. So mm, for one line, it will get converted into three line. So this is the normal Zeeman effect, and the normal Zeeman effect occurs when spin is zero. So there is no consideration of spin, only consideration of orbital angular momentum. Anyone has any doubt in this question? Basically, what we solved in this question is, due to the presence of external magnetic field, the orbital magnetic moment, there is interaction between E minus mu L, which is mu L is orbital magnetic moment, and B vector. So this was nothing but EH by 4 pi m into B. So because we know that Bohr magneton is EB by 2 EH cross by 2m. So here, due to this value, we got the splitting in energy is 5.21 10 to the power minus 7 electron volt, and from putting this value in this equation of delta lambda, we got the splitting is 1.17 10 to the power minus 3 angstrom. So in presence of an external magnetic field, a single line gets splitted into three lines, and the separation between this line is 1.17 10 to the power minus 3 angstrom, which is called as normal Zeeman effect or normal Zeeman splitting. So the next question, in this question, there is a similar question, but here the answer is, here the parameter we want is different. What magnetic flux density B is required to observe the normal Zeeman effect if a spectrometer, to observe the normal Zeeman effect if a spectrometer can resolve spectral lines separated by 0.5 angstrom at 5000 angstrom. So here, here what is, can anyone tell me? It is very similar to the previous question, because but in previous question magnetic field was given and we calculated this delta lambda. This is nothing but the delta lambda, that is the minimum separation between the two wavelengths which the spectrometer can resolve. So here delta lambda is given, but we want to calculate the value of B, and lambda here is, in the previous case lambda was 300, 600, 6438, but here lambda is 5000 angstrom and delta lambda is 0.5 angstrom, and we want to calculate the value of B. So in the similar way, we, in the previous, what was E? E was EH cross by 4 pi m into B. So this delta lambda was if we put the D value here, then it will be delta lambda. Suppose so, when we put here delta lambda is lambda square by c. Delta lambda is lambda square by c, sorry, lambda square by c into delta e. But what we calculated, what is delta e? Delta e is eh cross by 2m or by 4 pi m into b. So it is by 4 pi m into b. So here E gets cancelled out. delta lambda, we put here lambda, one lambda will be remaining. So delta lambda by lambda will be how much? Lambda by c e by 4 pi m into b. Then what will be the value of b? B will be d lambda by lambda into c by lambda into 4 pi m by e. So if we put here all the values, because d lambda is 0.5, lambda is 5 into 10 to the power 3 Armstrong, and c is 3 into 10 to the power 8. Lambda is lambda square, then e is 1.6 into 10 to the power minus 19 coulomb, and we put the value of m, then we get the total dipole moment in terms of Tesla. So if we calculate and get the value, it will be 4.28 Tesla. So if we place the atom in a magnetic field strength of 4.28 Tesla, then the spectral line separation will be separated by 0.5 Armstrong at 5000 Armstrong. So you can notice one thing. Can anyone tell me what you are noticing in these two questions? Because in one question the two questions were similar. In one question magnetic field was given and we are calculating the spectral, the separation of the spectral line. In one question the separation is given and we want to calculate the value of the magnetic field in order to find that separation. But in between two questions, basically what we can see here, the magnetic field was small, so the separation was small, but the magnetic field is here. In this case the magnetic field is coming in out of Tesla, but in the previous case the magnetic field was 0.009 Tesla, but here the magnetic field is 4.28 Tesla. So the spectral separation is 0.5 Armstrong, which is which is much larger than the previous case, because in previous case it was 10 to the power minus 3 Armstrong. So in order to get more splitting, we need to apply more stronger magnetic field. Understood everyone? Because due to the presence of magnetic field, the interaction between the magnetic field and orbital magnetic dipole moment results in the splitting of energy levels, and these energy levels, when splitted, give rise to different transitions of electrons. So as a result, the spectral lines, we get different spectral lines if we place an atom in an external magnetic field. Yes. Yes, yes, you can ask anytime. If you have any question, you can start. You can ask me at the start of the class. Also, anyhow, you can ask me. Please, what's your question? Yes, yes. Because K was the जो in Bohr's model, Bohr was given the model which in which the orbit of the electron was circular. But here, in case of Sommerfeld, the orbit was elliptical. So as a result, there was the introduction of another, because in circle, for a particular circle the r is constant, but so only there is only one coordinate which is theta. But here, in case of 1 minute, but here in case of Sommerfeld, Why to introduce that? The the orbits of the electron is not circular, however it is elliptical, and circle is one of the special case of the ellipse. So for for Sommerfeld, this was the shape of the orbital of the electron, and with nucleus placed at any one of the focus. So here there were two quantum numbers, one was n, one was k, because they introduced different quantization. So here the value of n and k was related. If n is 1, 2, 3 and this much, then k is less than equals to n. So for n equals to 1, k will be 0. Sorry, it will be, but n equal to 2, k will be 0, 1. It will be less 1, 2, like that. But here, but sorry. But here, as you notice, for L, if we considering orbital magnetic moment, that was k related to the orbits. But if we considering the orbital magnetic moment, as a result of after that quantum mechanics was developed. So due to the involvement of quantum mechanics, we found that electron when revolving in an orbital, it has some orbital angular momentum, and this orbital angular momentum is denoted in terms of L. So the split for n equals to 2, the value of L was 0, 1, that is less than n. So for L equals to 0, it was S, L equal to 1, it was P, L equal to 2, it was D, L equal to F, it was L equal to 3, it was F, like that. So due to the involvement of quantum mechanics, we get different value of L. So K basically here the since uh, there are two coordinates, like one is r and another is theta, there were two different quantum numbers. But here in order to explain the behavior of the electron, we introduced in quantum mechanics, there was involvement of the new orbital magnetic dipole moment or orbital angular momentum, and that orbital angular momentum also resulted in different orbital magnetic moment. Basically, if you study about the quantum mechanical treatment of the hydrogen atom, I hope it will be studied in the upcoming lectures. Then it will get cleared, because in this case also, what Summerfield had told, that the energy were depending only upon the value of L. There was no dependence upon K. But later it was found that they are also dependent upon L value. So there was a modification with you must be remembering, there was a term L plus half. So K and L are different. So basically K has nothing to deal with the quantum mechanics. K has different value, but here L was quantized. So L vector magnitude was L into L plus 1. So L into L plus 1 root over h cross. K is dimensionless. K is dimensionless, but here L is orbital angular momentum. So K and L are different. Similarly, for S also spin. After that, it was found that in case of, like in the G-man effect we discussed, it is normal G-man effect. But in case of anomalous G-man effect, there is spin is non-zero. So due to the involvement of spin, there was more splitting. So after that, spin was also developed. So electron not only revolves around the nucleus, electron also revolves, like in case of Earth. If sun is present here, then Earth is revolving around the sun, but at the same time, Earth is revolving around itself, with the axis of revolution is passing through the two poles of the Earth. So as a result, similarly for electron, there was spin. So as a result, there was another two quantum numbers, which is spin quantum number, another is spin magnetic quantum number. So S is spin quantum number, which is the value is S into S plus 1 root h cross, and its z component is ms h cross. So it is ml. So we there are different quantum numbers. So n is one quantum number, l is one quantum number. From l we found ml, and from s we found ms. So these are quantum numbers which represent their values are quantized. So basically this is the main difference. In Sommerfeld only considering about the k due to the due to the modification of the orbit, because the circular orbit was modified to elliptical orbit, but due to different quantum mechanical treatment there are new quantum numbers, and as a result we found the quantum numbers are like orbital quantum number and spin quantum numbers. Yes. Yes, it's obvious now, because we are seeing the effect of ML and MS if we place the magnetic field, if we space the atom in a magnetic field. Because in case of, in general, if this is the orbit, then this was the direction of the what is L? L is orbital angular momentum. So the direction of angular momentum is always perpendicular to the orbit. But when we introduce magnetic field, then in presence of magnetic field, because one more thing is what L is, what we call L. L is orbital angular momentum quantum number. But what is mu L or ml? It is angular moment. It is magnetic moment quantum number. Ml is orbital magnetic moment quantum number, and ms is spin magnetic moment quantum number. So these comes into picture when we are in case of, when we are present in a magnetic field, we place the atom in an external magnetic field. So when an atom is placed in an external magnetic field, mm, initially the orbit was like this, but when the atom is placed in an external magnetic field, the orbit starts oriented like, if we there was no magnetic field, then the orbitals like this. But when you apply magnetic field, then there will be, because corresponding to L we know there is mu L. What is mu L? Mu L is minus E by 2m into L. So due to the orbital motion of the electron, there was orbital dipole moment. But since there was no magnetic field, there are no interaction between the dipole moments. But when we place the atom in an external magnetic field, then due to the interaction between this orbital magnetic moment and magnetic field, then then there will be torque experienced by the angular momentum. So as a result, the orbit will be deflated, because due to torque, the initial direction of the angular momentum gets shifted. So as a result, we obtain, since in previous case the generally we were taking that the orbital magnetic moment is along the z direction, but when we apply magnetic field along z direction, then the direction of the orbital magnetic moment is different. So in order to calculate the contribution along z, we introduce new quantum numbers, which was spin magnetic quantum numbers. So basically ms or ml, what they represent? They represent the z component. So z component is ml h cross. So these are the new quantum numbers we introduce in case of external magnetic field. You must have heard about Larmor radius. Sorry, इसको what we say, Larmor precision. Like the when we apply Have you heard about Larmor precision? So in an external magnetic field, the orbits of the plane of the orbit gets oriented. So as a result, the angular momentum gets oriented. So there arises a new quantum number that represents the um, component of the quantum number along the direction of magnetic field, that is the z direction. So these are ml and ms. So L is angular momentum quantum number or orbital angular momentum quantum number, but ml is angular magnetic dipole moment quantum number. Yes, yes. No, no. Electron, like if the electron is revolving in this plane, then its direction is, we know that always for any surface, the direction of the surface is normal to the plane. So if the electron is revolving like this, then that will be the direction. So similarly, if the electron is revolving like this, then the direction of the orbital angular momentum will be in this direction. So when the magnetic field is present here, due to the effect of the magnetic field, the orbits of the electron gets oriented and they start revolving around the magnetic field. That is, if the magnetic field is, let me draw another figure. So what happens if, so initially this was the case, it was L vector. But when magnetic field was applied along this z direction, then due to the this L had also mu L component. So due to this presence of magnetic field, due to the interaction energy we just calculated is minus mu L into B. So this will also experience torque, which is mu L cross B vector. So as a result, this component L vector will be deflected in this direction. So L will be like this. So if we consider, so the plane of the orbit is in this direction, but again, suppose the plane of the orbit is like this, then in another direction. So it depends upon the strength of the magnetic. So it depends upon the strength of the magnetic field. What will be the angle between the two? So as a result, what is precision? Larmor precision is the revolution of the magnetic moment L vector or a spin magnetic moment S vector around the magnetic external magnetic field. So this L direction gets, so basically it is, we want to imagine in 3D. So suppose this is the magnetic field, then uh, this was the direction. So in after some time this was the direction after this one. So there will be a complete conical shape. So the orbit will be such that it's the normal vector, the vector which is normal to the surface will lie in the core. So due to this torque, the direction of the orbit gets deflected and it precesses around the magnetic field. Due to this torque experienced by the orbit in presence of external magnetic field. So the direction of the orbit gets changed. As a result, as a result, the orbital angular momentum L vector revolves around the magnetic field, external magnetic field applied, and forms a cone, which is called a Larmor precision. And there is also a frequency like which will be EB by 4 pi m, like that. EB by 4 pi m. Am I right? This is the frequency of the Larmor. precision. Okay. So everyone should ask doubts because if we question yourself, also you can be able to think about these things because Larmor's precision was not taught in the class. I will try to do this Larmor precision in the next session when I'll be taking the next session in the next Saturday. I'll be talking about this Larmor precision in more details because this Larmor precision results in the Jalmer precision comes in case of the external magnetic field, and due to this external magnetic field, we have different quantum numbers because only because due to the Lalmer precision, the L vector gets shifted and it forms some angle with the magnetic field, and so there are two new components like Z component because Z is the direction of the external magnetic field. So the Z component is again expressed in terms of ML and MS. For orbital it is ml and for spin it is ms. So there are two new quantum numbers in presence of magnetic field. So the sixth question what it gives, the question is, for an electron orbit with quantum number L equals to 2, state the possible values of magnetic quantum number mj. So here uh, basically this question may have some mistake, but let's try to solve this because it is L equals to 2. It is not L equals to 2, it is capital L equal to 2. So it is capital L equal to 2, not small l, it is capital L. So for quantum numbers mj, what we need to find? We need to find j. So for L equal to 2, first we need to find j. Here it is given for an electron, So there is only a single electron. So for a single electron, what is S? S is half, and it is given L is equal to 2. So the total quantum number it is L vector plus S vector. So this is vector addition. So these values will be 2 minus half to 2 plus half, and all are positive because j can't be negative. Its value like mj, they can be negative, but j can't be negative. So it will be 2 minus half. 2 minus half is 3 by 2, and 2 plus half is 5 by 2. So if an electron if an electron is orbiting in a orbit of quantum number L is equal to 2, then the spin of the electron is again half. So if for L equal to 2 and S equal to half, L is 2 minus half to 2 plus half. So 2 minus half is 3 by 2 and 2 plus half is 5 by 2. Then there are no numbers in between. So 2 3 for there are two different values of j. One is j equal to 3 by 2, another j equal to 5 by 2. So this 3 by 2 will be having some values of mj, and this 5 by 2 will be also having some values of nj. Then can you tell me for j equals to 3 by 2, how many values of mj will be there? Because 2j plus the number of mj values is 2j plus 1. So mj will be from minus j to plus j. So mj will be minus 3 by 2, 3 by 2 minus half, half. Similarly, for j is equal to 5 by 2, how many numbers values of mj will be there? 2j plus 1 for j equal to 5 by 2, 2j plus 1 is equal to 6. So it will be plus 5 by 2, 3 by 2, half, minus half, minus 3 by 2, minus 5 by 2. So there are six values of mj. So here in this question, it asks us to find the possible values of magnetic quantum numbers mj. Here it is magnetic quantum numbers, but they are angular quantum numbers like L. L is simple quantum number, but These are magnetic quantum number because in presence of external magnetic field, the component of this dipole moment, the components of these angular momentums along the magnetic field is given in terms of these quantum numbers. So for an electron which is orbiting in a state of L equals to 2, the possible values of mj is, there are 6 possible values. One is these 6 and this is 4. So total we can get 10 possible values of mj. These values correspond to j equals to 3 by 2 and these values correspond to j equal to 5 by 2. Then next question. This question is interesting. We can easily you can easily solve this question, but you need to understand what we want to do in this question. The quantum numbers of the two electrons in a two valence electron atom are n1 equal to 6, l1 equal to 3, and s1 equal to 0.5 or half. N2 equal to 5, L2 equals to 1, and S2 equals to 0.5. Assuming LS coupling, find the possible values of L and hence of J. So here in this question, LS and JJ coupling will be studying in upcoming weeks. But here, since it's given assuming LS coupling, so we can solve it because it's easier. Here it is small l1 and small l2 and small s1 and small s2, but here L is capital and S is capital. So what we so L will be L1 vector L1 plus L2. Sorry. So in case of LS coupling, these values are L1 plus L2 from mod up to L1 minus L2 from mod. These are like vector additions. So if L1 and L2 are given, so we can calculate the value of L from different combinations of these L1 and L2. So for 3 plus 1 we get 4 and 3 minus 1 we get 2. So in between with increasing 1 we get 4, 3, 2. So L will be 2, 3, 4. So we found the possible values of L and hence possible values of J. Again here S1 and S2 is given. We want to first calculate J, then after that J will be L plus S. So here L we found L is equal to 2, 3 and 4. So similarly S1 and S2 is given. So half plus half to half minus half. So half plus half is 1 and half minus half is 0. So the value of S is 1, 0. So if there are two electrons, then both can be either parallel or both can be anti-parallel, or one of them will parallel and one of them anti-parallel like this. So here in this case total is 0 because it is minus half plus half. Here in this case it is 0. Here it is half half 1. It is minus half minus 1. So it is 0 and one set is 1 minus 1 0. So this 0 corresponds to S is equal to 0 and these minus 1 0 1 corresponds to S equal to 1. So what we got? We got L equals to 2, 3, 4 and S equals to 0 and 1. So corresponding to this we need to calculate possible values of J. So what is the value so mathematically what is J? J is the total J is the total angular momentum. So J is L plus S. So this is L, this is S. We want to calculate values of J. So L is 2, 3, 4. So we can write L is 2, 3, 4 and S is 0 for for all cases S will be 0. Then again for S equal to 1, L is 2, 3, 4. So S is equal to 1, 1, 1. So here L is equal to 2 and S is equal to 0 and J is equal to L plus S. So here since S is equal to 0, so J is equal to direct 2, 3 plus 0 is 3 and 4 plus 0 is 4. So here 2, 3, 4 the values of j, but here in case of s equal to 1, so when we vectorially add these, then 2 plus 1 will be 3 and 2 minus 1 will be 1. So in between there will be, between 3 and 1 there will be another number which is 2. Similarly in this case sl plus s, 3 plus 1 4 and 3 minus 1 is 2. So in between 3 minus 4 and 2 there is another value of 3. Then 4 1, 4 plus 1 is 5 and 4 minus 1 is 3. So in between there will be another number 4. So for L equal to 0 and for L equal to 2 and S equal to 0, J is 2. For L equal to 3 and S equals to 0, we get J is equal to 3. For L equal to 4 and S equal to 0, we get J is equal to 4. But when S is non-zero, then for L equal to 2 and S equal to 1, we get 1, 2, 3. There are 3 J values. For L equal to 3 and S equal to 1, there are again 3 J values, which are 2, 3, 4. For L equal to 4 and S equal to 1, there are 3 J values, which is 3, 4, 5. So here as you can see there are many j values, so there will be different energy levels. So in case of a ls coupling, we get different spectral lines and there are different transfer rules. So in upcoming weeks we will be studying, you will be studying about different ls and jj coupling. Basically this ls coupling, what happens, first the individual angular momentum of the electrons get coupled to form the total orbital angular momentum L, and the individual spins, that is small s1 and small s2, they also get coupled to form the total spin angular momentum S, and after that this L and S get coupled to get the value of J, which is L plus S. So this is known as LS coupling. So due to LS coupling we get these different terms of J value. For L equal to 0, for when S equal to 0, L value is equal to J value, but when S equal to 1 there are three different values of J. So here in this case we are getting 12 values of j, that is 2, 3, 4. Then for again it will be 1, 2, 3, 2, 3, 4 and 3, 4, 5. So this is LS coupling. So these are also these energy levels can also be explained in terms of spectroscopic notations, which are also called as spectroscopy notations. We will be studying in the upcoming weeks. So the general the spectroscopy notation is given as 2s plus 1 L j. So for L equal to 2, for L equal to 2, what will be the orbital name? 0, 1, 2, 3. What is their values? S, P, D, F. So for L equal to 2, it will be D. So for S equal to 0, it will be 1. So 1D, 2. So similarly, this is 1D2. So again, this is for L equal to 3, it is 1F3, then it is 1F4, like that. There are different names of the spectroscopic notations of the energy levels. We will be studying about this in upcoming lectures. So we will be discussing more in details about this, how they are being calculated. So let's go to next question. Now again, this is similar to that of the again it is similar to that of the previous one where we did not calculate in transitions, but here it is given that the G-man pattern of a line consists of 9 equidistance components. So the G-man pattern consists of 9 equidistance components. So the transitions, so there are 9 transitions. So corresponding to each transitions, there will be each energy. So we want, so for this 3p2, 3p2, the upper state is 3p2. We want to determine the lower state. So this is 3p2. From this 3p2 level, if we, this is 3p2, so J value is 2. So corresponding to J value, there will be Mj values, which will be plus minus 2, plus minus 1 and 0. So Corresponding to each j, there will be 5 mj values. Similarly, for lowest state, there will be mj values. But here we want to calculate the lowest state term as it is given in this is the upper state term. So we want to calculate the lower state term. So basically in this case, the delta j or delta mj, we can say delta mj is equals to 0 plus minus 1. So and also delta s is equals to 0. So the transition occurs between the same multiplets, like here it is 3p2, the lowest state term will also be 3, that is for 3p2 2s plus 1 equal to 3, because as I said the spectroscopy notation is 2s plus 1 lj. So this is given 3p2. So this 3 is 2s plus 1, which gives s equals to 1. Since the transition rule satisfies delta s is equal to 0, so this lower level, for lower level s will be, since for this level s is equals to 1, for this lower level also s will be 1, because only when there will be transitions. But here it is given there are 9 equidistance components. So the selection rule is, there are 3 selection rules for mj, that is delta mj is 0, delta mj is plus 1 and delta mj is minus 1. So corresponding to these 3, if there are 9 components, so corresponds to each selection rule there are 3 components. So in the lower orbit, there will be 3 mj values. So there will be 3 mj value. 3 mj value is minus 1, 0, 1. So these mj values corresponds to j is equals to 1. So what we find? Generally we find is, since s equals to, here s equals to 1 then j equals to 1. So uh, j equals to l plus s. Since j equals to 1 and L plus 1, then what will be L? Then L will be 0. So the term corresponding to, suppose for a spectroscopic term L equal to 0, L equals to 0, S equals to 1 and J equals to 1. Then what will be the spectroscopic notation? Can anyone tell me? The spectroscopic term for which L equals to 0, S equal to 1 and J equal to 1, what will be the value in terms of 2S plus 1 Lj? For s equal to 1, what will be 2s plus 1? Then it will be 3. Since L equal to 0, here L we write s and j equal to 1. So if the lower level is 3s1, then there will be 9 transitions. So now we will see how these 9 transitions will be occurring. Suppose there are, suppose these are 5 levels. And this is 3 levels. So here it is 3p2, here it is 3s1. So here it was, here j is equal to 2, same j is equal to plus minus 2 plus minus 1 0. So what we will write here, to be plus 2 1 0 minus 1 minus 2. Similarly for here it will be minus 1, sorry, 0 1. So what we will get, the selection rule is delta j or small j is equal to plus minus 1 or 0. So from 2 there will be transition to plus 1 only. There will be no any there will not be any other transitions. But from plus 1 there will be, from plus 1 to plus 1 it is 0, from plus 1 to 0 the transition is possible, from 0, sorry, from 1 the transition is also possible to minus 1. Sorry, from plus 1 minus 1 transition is not possible, because as you can see here, 2 minus 1 is 1, so it is allowed. But 2 minus 0, 2 is not allowed, and 2 again, 2 minus of minus 1 is 3, so it is not allowed. So from 1, 1 minus 1 is 0, it is allowed. From 1 minus 0 it is allowed. So from 1 to 0 it is allowed, but from 1 to minus 1 it is not allowed, because 1 minus of minus 1 is 2, so it is not allowed. Then again from 0 there will be 3 transitions, from 3 to plus 1, from 0 to plus 1. I think the transition should be red. So from 0, the transition 1 will be to plus 1, from 0 to 0, and from 0 to minus 1. Similarly, from minus 1, the transition will be to, from minus 1 there can be transition to plus 1, because minus 1 into minus 1, it minus 1 plus minus 1 minus 2. So there will be only transition to 0, and there will be only transition to minus 1, because minus 1 plus 1 is 0. And similarly from minus 2, the transition will be from only minus 1, because minus 2 minus of minus 1 is minus 1, because minus 2 plus 1 is minus 1. So as you can see, for 3s is equal to 1 and 3p2, there are 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 transitions. So if the uppermost label is 3p2 and lowermost label is 3s1, then the transition will be only 9 transitions. So this transition corresponds to, suppose I am taking green color, then this, from, it is 2 minus 1, it is 1, another will be 1 to 0, it will be 1, then another will be 0 to minus 1, 0 to minus 1, this will be 1. So these green lines corresponds to delta j equals to 1. Similarly, you consider the blue line, from 1 to 1 it is 0, so this is 0, 0 to 0 this is 0, and minus 1 to minus 1 this is 0. So these three blue lines, this corresponds to delta j is equals to 0, and the remaining lines like these and these blacks, they corresponds to delta j is equals to minus 1. So for the transitions having 9 components, it is given the G-man pattern of a line consisting of 9 equidistant components. The upper state is known to be 3p by 2, determine the lowest state term. So basically, as you can see, it is 3p by 2, so 3p2, so 2s plus 1 is equal to 3. So here s is not equal to 0. So when s is not equal to 0, this effect is called as anomalous Zeeman effect. So as I had told that there are different transitions. So for three, so there are 9 components. So the 9 components will only be possible only when the ground state will be having mj values minus 1, 0, and 1. So these mj values of minus 1, 0, and 1 only corresponds to the j value of 1. So for the lower level from which to which the transition is occurring, this also, for this the j value will be 1. Since the selection rule is delta is equal to 0, so the multiplicity of this lower level will also be equal to the multiplicity of the upper level. So the multiplicity will be 3. So 2s plus 1 equal to 3 gives s equals to 1. So for this s equals to 1, and since j equal to l plus s, and we know that s equal to 1 and j equal to 1, so l becomes 0. So L0, S1 and J1, they give rise to the spectroscopy term 2S plus 1 Lj, which is 3S1. So when the transition occurs between two labels, which is 3P2 and 3S1, then there are 9 components, and these components corresponds to the transition rule of delta j is equal to plus minus 1 0, because in case of norm and in case of this Zeeman pattern, the significance is only of the small j or nj value. So the L values and the L and S values are not considered here. So correspond. So depending on upon the J values, the selection rule is delta J plus delta J is equal to plus minus one, plus one minus one and zero. Corresponds to this selection rule. There are 9 transitions. So these 9 transitions, 3 transitions correspond to delta J is equal to 1, 3 transitions correspond to delta is equal to 0, and another 3 transitions correspond to delta is equal to minus 1. So total 9 transitions occurs, and that so this single line, when there is no magnetic field, it was 0. But in case of magnetic field, this single line gets splitted into 9 lines. So you can see there are 9 lines. So this single line gets splitted into 9 lines. So this is known as Zeeman effect. So I think we should stop here. We will discuss other problems in the next class or next interaction session. So thank you for attending this session. So if you have any doubt, you can ask me now. Anyone? If you have any doubt, so I'm stopping here. Thank you all.